Okay, so I know we are starting after a long gap. I think we are starting after 3 weeks. Uh, so does anybody remember? Anybody remember? Let's see first. How many of you remember what we had done in the last session? We'll start with that. Let's see how many of you remember what we have been doing, because today is a very big step, and I think this is where we start getting into the big time AI using PyTorch. Because last time, anyway, what did we did an introduction to PyTorch. That's correct. We actually did by and large the crude backpropagation, the from scratch. But only thing is, instead of writing Python code, we wrote the code in PyTorch, and we demonstrated that some of the things like calculating the loss functions, calculating the derivatives, multiplying matrices, and all that became very easy. And today you will see how easy is it to design a network. No, okay, good. So, so today will be a very crucial session where we'll talk about how PyTorch gets used. And PyTorch, of course, last time we started talking about PyTorch, but today we will design a reasonably complex, not very complex, but reasonably complex network using PyTorch. And I'll walk you through some pieces of code as usual, just so that you understand how a network is designed using PyTorch. As we see the network, we will design it. Then you'll see how easy it is to do backpropagation of the error, applying the gradients and weight updates and all that. How easy is it to do optimization? Because we have been talking about momentum optimization, we have been talking about learning rate decays, all of that. So we will see how simple it is now using PyTorch libraries, and this will be the takeoff point for you to start designing reasonably good networks and all that. So here's to your start of your journey, big time journey in creating networks, neural networks. The same theory can be used later for creating CNNs, for creating transformers, for creating many different kinds of networks. The same sort of code can be utilized. So I'll try and make the example very simple and easy to understand. We'll walk through some libraries, walk through some code, and then I'll show you some graphs and that kind of stuff, some plotting. But it's important that you understand what code is used and what code gets done. So we will send you a PDF file, which we will walk through, at least some of the PDF file. We'll walk through the rest of it. You can do it on your own. Okay, we'll just wait for you to get the PDF. We are just sending it in a few minutes, and then we will start, because I'm going to use that PDF as a basis for designing the network. Okay, looks like the PDF file is shared. So as soon as you start getting it, just open it, and if one or two of you open it, then I can start. Just confirm whether you have received the file and you have been able to open the file. Open. Okay, good. Okay, so I'm now going to start walking you through the code, and as we walk through the code, I'll give you an insight as to what all happens. Okay, so it's not going to be a very heavy session. You will understand how simple it is using PyTorch libraries, and yeah, it's pretty easy to design stuff. So in this example, we are going to first of all generate our own data set, which is rare. Generally, you get a data set and then you train on that data set. But here we are going to generate a data set. Okay, no, I forgot actually. I generally start with a summary of how our startups are doing. Well, the startups have been taking a little bit of rest in the last week or two because of the new year, and we have been off kind of. So there is no new update, but yeah, one thing is important. I don't know whether you're getting our journal, our startup journal. We call it Paradigm Chronicles. Now, this is important for me to get because I don't know whether our distribution is working correctly. Any one of you has seen or got the Paradigm Chronicles? Yeah, one I think has been released so far. The second one should come to you. Okay, good. At least some of you are getting. Now, if you're not getting, you will have to go and see. I think you're getting it on WhatsApp or you're getting it. How are you getting it? On mail? Is it on your official mail? That is the college given mail, edu mail. Yeah. Okay. So that is where you will get it. So it should come on your edu mail, and you should be able to see So you should be able to see the paradigm. We'll also host it on a site and get it done soon. It is still in its inception and all that. Jamie?
We have planned on 20th for recruiting to the paradigms.
Oh, okay. That is going to start. Yeah. Oh, okay. That's in the cards. We'll soon start that once. I think we will.
The PS test is scheduled on 9th for
I think it is done at different places,
yeah.
different times. So you will soon come to know what the process is and all that. Yeah, I think it's handled by a separate group as far as recruitment is concerned. Yeah. We don't know the date. I think
PS exam date is 9th.
PS date is 9th, but when is the date for that?
That
I think that's a separate group which will handle that. So the recruitment to that. So I think we will tell them to get you the dates. That also, I think the group will communicate. Okay. So today we will we will generate our own data set. We are not going to use any third-party data sets. Then we'll understand how data loader works. This is an important piece of design. Which libraries we use for data loader, that is the torch.utils.data. Then we'll define a multi-layer perceptron, which is basically an ANN. Then how do we do the training, and how do we do the testing, and how do we do some plotting? Okay. So this is some things which we'll learn today. So how to create new data sets, how to work with the data loader, how to design a network using PyTorch very simply, how to do backpropagation, how to do the activation functions, all of that. And then what is the, how does the training of that network happens, and how does it test, okay? So now, this piece is important. I'll go through the libraries. These libraries get used again and again. So it's important that you know. Okay, so the main important library is the torch library. Torch.nn is the neural network library. The optimizer, which is the atom optimizer or the momentum optimizer or whatever, which decides how the weights are going to get updated, that comes from torch.optim. It's called the optim class. So we're going to use that. Then we are going to use from torch.utils.data. We are going to use two things. One is called data set to create a hypothetical random data set, and data loader. This, as I said, is going to be an important piece. Then there is a very interesting way of creating data sets from sklearn.datasets, which is called make moons. I mean, this is an example of creating one type of data sets. Okay, there are many others. So example of creating data sets is make moons, make the crescents, two crescents. Okay. Then we are going to use how to do splitting of the data, and we'll briefly talk about that into train and test. How do you split data and how do we make that happen? Then there is some amount of transformation of the data, which is scaling of the data. So we are going to use standard scaler for that. You will see all of these as we use them. Then there is the matplot Python plotting, which is the plotting library. Some of you may have seen this already. And of course, our good old NumPy for managing the Python arrays. All the Python arrays are managed through the NumPy. So these are some of the common set of libraries which we use often. And these are a good set of starting libraries. Some of them for generating data, some of them for loading data, some of them for transforming data, that is altering data, scaling data, some of them for splitting data in a train test way, and something for plotting data. So this is a very classic thing in any neural network. Most neural networks will have these kind of libraries, maybe some less, some more, but this is a fairly good collection. So this program, keep it with you carefully because it will come useful for creating more stuff or understanding more stuff nowadays. Okay, so I think that's a small gist without taking too much, wasting too much time here. Let's get down into the working of the libraries and see how a Python program is created for a multi-layer perceptron. I'll describe the perceptron as we go. Perceptron means an ANN, what we have been calling as ANN. Now, before we start, there are some hyperparameters. The weights of various layers are called the parameters, and things which don't change, weights get updated with every batch, right? Batch-based update, whereas these don't get changed. These are called the hyperparameters. Well, there can be more, there can be less, and I'll try and talk about it. So there is a random seed. I'll tell you later why random seed has to be fixed. I'll come to the relevance of it the moment we start using it in a program. Batch size is 64. That is the size of each batch. Typically, batch sizes you see in business are 16, 32, 64, 128, like that. So here, each batch, that means at any point, we are going to look at 64 samples of data. So that is 64. LR is called the learning rate. So we are starting with a number of 0.01. Depending upon the optimizer that you use, the learning rate may change. Learning may decay as the learning progresses, as I described last time. So that is a learning rate. And epochs, we intend to run training for 80 epochs. Then there are some parameters like hidden units. These are the number of neurons in the hidden layer. So in the earlier toy examples, we used to use 3 neurons in the hidden layer, 2 neurons in the hidden layer. Now, because we are doing a proper multi-layer perceptron, a proper ANN, you can see the number of hidden units has gone up to a more realistic value of 64. Now, test size is when we have a certain amount of data, let's say we have 100 samples of data, we use 75 samples for training, and we keep aside 25 samples for testing whether our training is working well or not. So while training, these samples are never seen by the model. These are used to check how the model is doing. So it's like saying 75 are used for training, 25 are done inference, and then the results of that inference are checked and seen whether it is improving epoch after epoch or whatever. So that's basically the quantum of data or percentage of data we want to set aside for testing. That is what it is. Now we are going to use some standard way of generating data, and after that, to add a little bit of randomness to the data, to scatter the data a bit, to shuffle the data a bit, we are going to add a bit of noise. This is very common. So while we generate the data is in two reasonably well-structured crescent moons. But what we are going to do is we are going to add some noise to it so that the data is not clean and our problem becomes interesting. If the data is very cleanly separable, then the data has no fun. Our algorithms don't have fun. The problem is only when data is not so cleanly separable. So basically, just to give you an idea before we go to the next line, the kind of data we are going to use is in the shape of two crescents. This is one crescent, and I guess this is another crescent. Okay, this is one crescent. I hope I'm able to draw the crescent reasonably well. So this is the data. So it's part of one crescent or the other crescent, and we have to judge whether it's a part of this crescent or this crescent. So that's basically the thing. The whole thing is covered actually. There's not so much left here. So we have to judge whether it's in this crescent or this crescent. So we are going to work with that sample of data. Okay. Now, so this is very clean. Now we would like some of this data to merge with this data and all that, so that the algorithm has some trouble separating out data and therefore a challenge. Now, this line is super important, very important line, and I hope you understand this line. Now, the device on which we are going to do the computing. Now, PyTorch automatically chooses either CPU or GPU, depending on availability. And this is the line which makes it do that. So PyTorch.device, you're telling Torch to use a device, CUDA. CUDA means, as some of you would know, if you have been following our earlier sessions, that I want to use GPU if Torch CUDA is available. That means this machine on which you are running this program, as we'll soon start. I have been promising for you to start the Tantric, but we have not done that because we have been still talking about theory and all that. And anyway, you will have a lot of Tantric practicals as we go into the skilling part of this semester. So that's why, we don't have to worry so much about the practical, but you will do a lot of practical. So here what is happening is torch.device CUDA, if torch.CUDA is available. I hope you understand what this line means is that if this PyTorch library is running on a system on which GPU is available, then we are saying internally the PyTorch library should use CUDA. If it is not available, it should use a regular CPU. So it is like saying you are telling PyTorch, go figure out, check, the PyTorch will check, talk to the underlying OS, and once it talks to the underlying OS, it is going to ask the question, Mr. OS, do you have this GPU support integrated? If you have the GPU support integrated, then my device on which I'm going to do this PyTorch programming is going to be a CUDA device or a GPU device. Otherwise, I'm going to make do with a CPU program. Obviously, as we had demonstrated earlier, if you try the program on a GPU, you can use parallelism and all that, multiple cells, multiple neurons, multiple weights can be computed, matrix multiplication happens much faster. We had talked about all that in the earlier weeks. So that will happen. Otherwise, if you're running on a machine which doesn't have CUDA, which doesn't have GPU, you're going to be happy with a CPU. So that's what this means. Then we are saying, now these two lines are important. Remember, we had defined a random seed. Now we are going to ask our libraries, soon, we are going to ask for some like data like this to be generated with some amount of noise and all that. So while generating those things, the way the data is going to be generated randomly. But to ensure that all your random, our random, somebody else's random who uses this program, though it's random, it shouldn't be different from your random, and my random should be same. Now you know how that happens, right? If you seed the random number generation by a common seed that we have fixed as 42 and use that later, then your random and my random becomes same. So though we are asking data to be generated randomly, there is no difference between, there is no randomness between you and me. The data is random, but your random and my random is exactly same. So that is what we want most of the time for testability, provability, uniformity, all of that. So that's why we are seeding both the torch library as well as the NumpY library, both with the same random seed, which is this random seed. The way to do it is different. So on torch, we directly call the manual seed method and pass random seed as a parameter. Here we say np.random.seed, go to the random package of NP or random library of NP, and then call the seed and do the random seed. So this is just two ways of doing it, right? So these are an explanation of the hyperparameters. Now I think we are going to get into the meat of the code, and hopefully we'll get a hang of what's happening. So the first step is going to be creating the data set. So I think we will scroll up and see whether we can get the step one. Okay, good. So this is creating the data set, random data set, and let's see how this happens. Okay, so make moons, that is make two crescents of data, and how many samples should we generate of data spread between these two moons? It will make two moons and spread the data among the two moons. Either it belongs to this moon, this crescent, or this crescent. Make moons, number of samples we want to generate is 1000. Noise is, we don't want it to be cleanly. That is, some of this data will get mingled with this, some of this guys. So if this is all and this is all, I mean, this is just to represent data of two different moons. Some of these will appear here and some of these will appear here. If you get what I'm saying, this is because of the noise. 25% of the samples, there will be intermingling. Rest of the samples will be clean for the upper moon and the lower moon. So this make moons generates those moons, and they are going to be totally 1000 samples of data. So are they going to be evenly distributed? Maybe, maybe not. And noise will be added so that this intermingling happens. And the data itself is very random. Random in the sense it can belong anywhere in the moon as long as it's random. So, and here what we are doing is we are ensuring the data types, that the X data type is float. It has two coordinates, obviously. This is on a two-dimensional plane. So all X is two-dimensional. Basically, it gives the horizontal coordinate and the vertical coordinate. And Y is what? Y decides what kind of moon it is. Is it moon 1, 2, or 0, 1? Whatever the mechanism we use to say which moon does it belong to, upper moon or lower moon. So we are going to have this data generated, and basically it will belong to one of the moons. I think we will play this code and show you. We will just try and see if we can run this code and show you what really happens, because that would be pretty useful to see, I guess. Okay, we'll just play it and show you if we can. We are using an online Python story to do this. It will take a bit of time, I guess. There's no matplotlib. Yeah, just wait for a few minutes. We are just settling it. X uppercase.
Supplication, while this is
This is y and our is x.
first one is X, so second one the binary zeros and one is the Y.
Mm.
And
Let's see if we can create a moon here. अरे इसका
the remaining code, if we add, we can see that later.
no, I'm just seeing whether if we connect all the ones,
Oh,
should be like this. See, there are two moons.
one is X coordinate, one another is Y most.
This is x, this is y. Yeah.
Uh,
This is the horizontal and vertical
but
coordinate.
these are 1,000 samples.
These are y values. 1,000 samples. So these are spread in two moons. Now I'm not able to make out two moons here, but these are two moons, but they are all randomized.
Yeah.
Okay, I think you will get a hang of what the data we are dealing with, just so that you get a understanding. See, for x there are two coordinates. This is the horizontal coordinate, this is the vertical coordinate. See, this each is a pair. So x is all the coordinates. It's a two-dimensional data set, and at every so imagine there is some kind of a picture here. Just think of it as a picture. That's the best. So the picture has two coordinates, obviously, to define every coordinate, and y is the value sitting at that coordinate. So the value is either 0 or 1, and our job is to predict, because we have created the moons, is to learn the pattern and predict there should be a 1 or a 0. So that's what we are supposed to do. So I hope you get there. Yeah, if you get remove the noise, maybe it will come in a crescent shape. That's a good idea. Let's try removing the noise and see whether we are able to see the two crescents the way they are. So we'll make noise 0 and try this again. Are they more crescent like? I'm still not able to see the.
That is each sample most.
Yeah. Once the samples are arranged,
Mm.
see, the samples are also randomized. They are not arranged in the appropriate x and y. Once you arrange them in the x and y order, then the moons will be formed. Okay. So you won't see even if you remove the noise, because the data is not created in the proper x and y order. The data is created. There are two moons of data, and it's a randomized. The data has been randomized. It is not our random data and your random data will be same. That's all. But which is what we don't know. I mean, that needs to be organized and judged. So there are two dimensionals of data, and the data values are there. They may not be in the right order. They'll come in the order once everything is set. When we plot it in the correct way with this x and this y, we will see it. But right now the data is not plotted. These are just values of y. We have not plotted them as per this. So let's bring back the noise, and when we plot it, we will see it in the correct order. Okay. So I will show you the plot a while later. Okay. We have not plotted the data. Okay. This is take them as 1,000 samples of data. That is 1,000 1,000 horizontal and vertical coordinates. Each point belonging to either the first moon or the second moon. Okay. So that's how the data is organized. Our job is to make the pattern clear using an ANN. Okay. So let's now proceed with that. let's proceed to the next step. It's good that we have now a Jupyter notebook working so that we know what each step does. Okay, now we have made the data into float 32, as you can see, and y has become integer data, which is 0 and 1. Okay, so that is the answer. So here, if you want to mix it with the attribute theory, the way it is there are two attributes, the horizontal coordinate, I'm calling it the horizontal coordinate, and the vertical coordinate, and against that there is a value of y. So that is how the data is. So there are two attributes to that data, and there is a y which decides which moon does this pair belong to, and the pattern has to be discovered. Okay, so now we will just scale the data, and you will see what happens after the data is scaled. So we are using a scaler for the data. You see there. So you see we are using a standard scaler, and now we are scaling the x and y coordinates. See, currently the x and y coordinates are all over the place. They are not normalized to the 0, 1 space. So now we will scale it, and then let's print x again so that you know what scaling is doing. Let's look at the data first, and just let's add these two lines. So we know before scaling and after scaling, what does scaling do to the data? First print x values as they are, then scale, and then print. No, then say before scaling, after scaling. Yeah, let's see what scaling does. Before scaling, this was the tuple.
There is a small change in the value.
No, they need to get. See, they are brought into that range. Here it was 1.197, 1.74. They were exceeding, no? Now they should have been. No. I don't think the scaling has worked correctly.
X values after scaling, they're into negative values here, sir.
The negative values are still there.
Yeah, after scaling.
Did you scale correctly and print correctly?
Yes.
Just a minute. I don't know what is going wrong. Oh, okay. I messed up. So what the scaling does is not really bring it to any range, but it kind of normalizes the values. I'll tell you what it does. Basically, it takes the mean of the values which are there before scaling, and subtracts the mean and divides it by the standard deviation. So it brings it into a Poisson's distribution. The values are brought into some kind of a Poisson's distribution after scaling, after transform. So the way is after scaling, let me just write the equation here. X bar is equal to x minus mu by the standard deviation. So this is what brings the data into a Poisson's kind of a distribution. It subtracts the mean. Mu is the mean, and this is the standard deviation. So it computes the standard deviation, and this computes the mean, and it brings it to that range. So that is what the values are after scaling, and they are brought to that order. Okay. So yeah, you can in fact if you want, compute the mean from the scaler will also tell you the mean. The scaler will also tell you the standard deviation which has computed. There are functions to do that, and it is done. So basically the data is brought into a given range, and basically kind of normalized after scaling. Okay. So let's move on. So we have scaled the data. Now there is an important step that happens here. This is a very important step, which is also very common. Yeah, in this case, scaling is a little bit of overkill because the data was not very wide. Okay, now I'm looking at the train test split line. What does that line do? So train test split is an important method supplied by the sklearn skillkit learn library. What it does is it takes x, there are so many samples, thousand samples, y also there are 1,000, and splits it into a test data set and a training data set. X training separate, X testing separate, Y training separate, Y testing separate. What we can do is we can test the length or size of this and check what is the size of X train and what is the size of X test after this. So you should see it in the range of 75-25. Okay, so it's splitting the data into a training data set and a testing data set, and let's see whether that is achieved. Okay? So let's do that line and check. We are going very slow because I want you to get what is happening, because this is the first big program we are doing, and this is very common what we do. So we are splitting the data into two parts. Some data we'll use for training, some data we'll use for testing. I think we can skip those printings. Let's just print. And let's just print the size or length of train and test. X train length or size. No, length is not that. LEN is that. Or size V. So now, as you can see, the size is coming as 1500 for train, and oh, that means it has generated 2000 samples, and 75% of 1000 samples for the first moon and 1000 samples for the second moon. Okay, so that's the interpretation. So it has generated 1000 samples for the first moon, 1000 samples for the second moon, and X train size, Y train size will be same. You can check that, and X test size should be 500. X test dot size. The X train and Y train sizes should be same because it's 1-to-1. Yeah. So X train size is 1500. X test size is 500. Y train size is 750 and 250. No, there's something wrong. No, noise is 0.25.
Test size is also 0.25.
Hmm?
Test size is also 0.25 and noise is also 0.25. Both are
No, test size is 1/4 that it got.
But why X train got double the size?
No, how can it be that Y train size should be same as X train size, right?
After transforming, will it get double? So
scalar dot fit transformer X.
after scale.
No, it's transforming just as mean and all that. Shape is same, not size. Oh, we need to say shape. Oh, you're right. Extend dot shape, what will it give? Just say extend dot. Because see, there are two, no?
Yes.
For X, there are two pieces of data. Oh, you're right. You're right, Satvik. We are messing up. X train, see, there are two, X and horizontal coordinate and vertical coordinate. So all of that is getting counted. So actually, we should say X train dot shape.
Size will be always, because there are two coordinates, it is double, and there are only 1000 samples. This is correct. You should say ytrain dot shape also. No, ytrain dot shape. Always they say shape, don't say size. Good, Satvik. So the way it is y is a one-dimensional matrix, x is a two-dimensional matrix. So x is 752 and x test is 252. That is what it is. We by mistake had said dot size, so it was multiplying and we were getting confused. 750 and 250 is correct. So altogether there are about 1000 samples. And 1000 samples are spread between two moons, and one moon is having probably 1500 and 500. We don't know because it may not always be correct because of the noise. Okay, so we can actually measure that too, but we'll come to that. Now let's move to the next line. Yeah, now comes a little bit of important thing. So far we are just doing, now this is a little conceptual, and pay close attention to this part of the code. Yeah, just look at this part of the code. So the class moon dataset, now we are creating a data loader, or we are creating a data set for the data loader. Now let's understand what all this means. Okay, let's go very carefully. Let's understand this. Class moon dataset is derived from the dataset class, which is a standard Python dataset class coming from the torch libraries. So we are creating our own dataset. Now, as a dataset, there are three methods expected. One is the constructor, which basically just sets the data. So to the constructor, we are passing the original x samples and the y samples. Remember, x is two-dimensional. And what are the dimensions of x? It is 752. That is the dimensions of x. And y is 251 or just 250. You can say it's a single-dimensional data. So y is single-dimensional data, x is two-dimensional data. And now what we are doing is, so far they are numpy arrays. Now we are really getting into torch, where we are converting that data from being a numpy array, which it was so far, into a tensor. Now a tensor is capable of storing a gradient, doing back propagation and all of that. A numpy array is just a dumb array. A tensor is where actually the stuff starts. So we are converting this data x, which is so far only a array, into a tensor, and we are indicating the data type also, that it should be float 32 or whatever data type you choose. So now the data is being transformed into a tensor. So it's becoming a tensor. Tensor has the ability to store gradients and all. Remember, we had a dictionary for every neuron. Remember, here in place of that, we actually use the concept of the tensor, which is capable of storing the gradient, accumulating the gradient, doing back propagation, all of that. So in order to be able to do all of that and have a multidimensional data, it is going to be, that's what I am doing. So I'm converting that data from an array thing into a tensor thing, which is capable of doing all the rest of the stuff which is required for an ANN. Y also, we are transforming it into a tensor. Then we are supporting a method length, which is necessary for every data set. What is the size of the data set? Basically, it's called the length of the data set, which is return self dot length is a method supported by tensors. Since x is a tensor, you say length on the tensor, it will give you the size of that tensor, the number of elements in that tensor. So that is this.
And then given an index, this is the most important method, given an index into the tensor, we should be able to supply the value. So x idx is what gets returned. So the two-dimensional data for x at a given index, at a given row, gets returned, and y at a given in a row, you can think of index as a row, and that gets returned. So if you're looking at a particular sample of data, this is how you look. Now this will become useful, and I'll tell you how it engages in a moment, we will see. But these are the primary methods for a data set. You need an init method, and you see the double underline method that makes it a special method. We need a length method. We need a get item method. These methods will be invoked internally. We will not directly, most of the time, invoke the methods. They'll be invoked by the data loader. I will come to that in a moment. But anytime you want to build a data set, this is the standard procedure. This, you have to have a init method, which is the constructor for the data set, and then you have to have a length method, which tells the size of the data set, and you need to have a get item method, which basically tells us get a particular item at a particular row number or an index. So that's the three mandatory methods for a data set. There are some more, but as long as you have these methods, you're okay. So these are the three methods any data set must support before it becomes a AI based data set, becomes useful for training or anything. Now see what we are doing. We are creating two data loaders, a train data loader and a test data loader. You will see what we are doing there. Okay, now I'm going to explain the data loader. Listen very carefully. We need the whole code. Just a minute. We will give you the whole code. Shuffle is equal to true. Okay, so these two lines mean this. Now this is a very, very potent line, and I think we'll have to explain this in detail. Now we are creating a data loader using a data set. Always a data loader internally uses a data set. So if you understand this code, while creating the data loader, we are instantiating a data set internally to the data loader. Batch size is equal to batch size, whatever that parameter is, which is 64. Shuffle is equal to true. Shuffle is to spoil the order. It's up to you whether you want shuffle or you don't want to shuffle. Generally, it's during training at least, it is considered good to shuffle data. So what this is going to do is, it is going to instantiate a data loader, because what's going to happen is, this is a data set which is going to get created. And every time, whenever the data loader is asked to give data, or whenever I fetch, which will come later, whenever we fetch data from the data loader, internally the data loader is going to talk to the data set to get the data. And how much of data it is going to get? Every time it is going to get, let's say the batch size is 64, it is going to get 64 rows of data, the data and the Y, that is the dependent and the data, it is going to get 64 at a time from the data set. And that is what the data loader is going to do. So it's like this. The data loader is a mechanism to get data into the program. So the program talks to the data loader to fetch data. Every time I ask the data loader to fetch data, the data loader talks to the data set it has been instantiated with. The data set contains all the data, and the data loader talks to the data set and says, Mr. Data Set, give me 64 pieces of data every time. So the first time I ask you, give me the first 64. You maintain, or the data loader maintains an index. Okay, it has asked 64. So the next time it asks, so first time the indexes it will use are 0 to 63 on the data set. Remember, there was that get index. See this get item method with index as a parameter. So it will do retrieval of first time 0 to 63 because batch is 64, and retrieve the data from the data set and bring it into the data loader and give it to the program. And this will happen when the program asks to fetch data from the data loader. It will talk to the data set, retrieve index 0 to 63 using this method. And because the batch size is 64, next time it will retrieve from 64 to 127. This is the indexes it will retrieve. Next time you do a fetch. So automatically the data loader is smart. It maintains a state, and state means the index it was last retrieved, adds 1 to that index and retrieves the next batch from 64 to 127, these indexes. And the data set then supports this logic by implementing this get item method, which every time gives that many rows using the index. So this is fundamental to understand how the data loader is built using data set. And during testing, it may not be important to shuffle the data. Training, because it's done again and again, it's better to shuffle the data. But testing, not so needed. And this is the way it is done. Testing also same thing. The same results are brought, X test, Y test, and this is the only thing is the data loader is used. This test loader is using inference, and train loader is using during training. That's all. But the way they work is the same. Okay. So at this stage, I think it is a good time to ask you whether so far is the story clear. We have seen how to create some fictitious data. How does that data look like? And then how to define a data set, and then how to define a data loader, which engages with the data set and retrieves the data. All that we have seen so far. Now we are going to get into the creation of the network itself, the MLP, that is the ANN or the multi-layer perceptron. So I think it's opportune to create a small poll and check how far have we come. Yeah, we're just doing a poll just to check. Okay, I think we got significant, almost 50% of the votes. I don't think we get more than that. Okay. Anyway, so overwhelmingly you have understood. So let's move on. Now we get into the meat of the creation of the perceptron. Let's understand how do we create the model or the perceptron. Okay, now this is the important piece, and let's see how you can get it. Wow. Okay, I hope the screen is legible, and anyway, you have the code. So now we are getting ready to create the network, the ANN itself. See how easy is it to create it with the way it is. So the way we want the network to be created is self, of course, refers to the current object. Input dimensions is 2 because the horizontal and the vertical coordinates are there. So input dimension is 2. Hidden units are the number of hidden units in the layers. That is the hidden neurons in the hidden layer. Okay, there's going to be one hidden layer.
Tell about the tensor.
We'll come to the tensor. Number of classes is equal to 2. I'll explain this. Number of classes is 2 because Y takes 2 values, 0 or 1. So the output consists of only 2 classes. That means the data is classified either belonging to one moon or the other moon. So there are only 2 classes. Dropout, I'll explain dropout in a moment, just in a moment. Okay. So now let's see how the network is getting created. See how simple it is using PyTorch to create a network. Let's go line by line and understand the network creation. Super.init is just invoking the base class constructor. All models are created using by deriving from nn.module, and then we have nn.superinit. Super.init, we are just calling the base class constructor like we normally do in languages like C++ also. We always call super, or Java calls super implicitly. Then we have self.net. This is what we are defining. Net is our network. We are creating the network. The ANN is getting created sequentially. we can also create something in parallel, but that's not the point now. So we're creating sequentially, and let's see what is getting created, right? So input dimensions is 2. Okay, so they're going to be, for each sample, they're only going to be 2 values, x and y, or call it horizontal coordinate and vertical coordinate to make it simple. Then there is going to be hidden dimensions. I think hidden dimensions, if I remember right, are 64. Okay, so this is the first network which is created. Okay, and then there is this ReLU activation. See, so far we have been using sigmoid activation. Now we are using ReLU activation. ReLU activation looks like this. Okay, I mean, this is how Z is done out of how A1 is done out of Z. This is what it is. So this is the activation, which is ReLU. Now the output is also going to be 64, of course. Now what we are going to do is we are going to drop out a certain percentage of that. Now we don't know, some of these neurons, of the 64 neurons which are on the output, 20% of those neurons are going to stay silent for some time. Okay. Now which 24? Which 20%? 20% is about 12, right? 12 or 13. I mean, if you see 20% of this 64 is about 12 or 13 neurons are going to be at randomly chosen, are going to be asked to keep quiet. Okay, I'll tell you why they're going to be asked to keep quiet in a moment. And only the remaining stay active. Then that is what dropout does. I'll elaborate at length. And then there is again the next layer of the network, which reduces from 34 to 32. So from 64 to 32. See this N linear, hidden to hidden by 2. Okay, so that goes to the next hidden layer, reduces this by a half. So now there are 32 neurons here. Again, there is a ReLU activation. We used to use sigmoid activation, but now we use ReLU activation. Now again, there is a dropout. Again, out of these 32, maybe 20% of them are asked randomly at times to keep quiet. And then again, there is a dropout. And then again, there is from hidden by 2, that is from 32 to 2 classes. So finally, there are only 2 classes in the output, 0 and 1. So now this is how it is done. Okay, so this is basically the network. Okay, now and now let's see. So there are 2 here, 64 here, 32 here, and 2 here. Dropouts are randomly chosen at times to say you will keep quiet, but I'll come back to that. Now let's understand this network in a little more detail. Okay. Now let's see how bright some of you are. There are always bright guys in KMIT and all our other colleges. Can you tell me how many weights are there? Total number of weights or parameters in this network. How many weights or parameters are there? Can you tell me, now that the network is in front of you and I have created the dimensions of that network and I have told you what the network is. Now, can you tell me how many weights are there in total number of weights which are there in this network? Now, tell me overall how many weights are there? There are 2 hidden layers you can see, not 1. Anybody? How many weights are there? Total number of weights. No, not 2. Or you can write the equation, I don't mind. Okay. Some of you are trying. No, you can write the equation. Somebody wrote it right. Yeah, good, Satvik. You're a smart guy. Satvik is second year or first year?
Satvik, are you first year or second year? Second year. Okay, good. So Satvik, you got it right. So the number of weights in this layer, this is the hidden layer, this is the input layer, and this is the first hidden layer, is how many? 2 into 64. Each one of this is connected to, see, this is connected to this. So there are 64 into 2. Correct? So these many weights are there in this layer. So that's the first part, 2 into 64. Plus, how many weights are there here? Same thing, 64 into 32. Plus, how many are there? 32 into 2. Now, let's ignore bias. Let's ignore bias. Okay. Let's forget bias for a moment. No, let's ignore bias. That's one always added. But okay.
They're worried about the bias.
Ignore the bias. We can always add one. Don't keep the math simple. So this is 128. This is how much?
2048.
Is this 2048? Yeah.
Yes.
2048 plus 64.
60.
This comes around 2,300 odd.
2240.
Does it come 2240?
Yes.
128, 192.
192 plus 2048.
I think this is right. 2240 is
Yeah.
correct. This is the total number of weights, okay, in this whole network. So this is how easy is it to design the network. So you have the input, which has only 2 inputs. We know that because our input has only horizontal coordinate and the vertical coordinate. So there are 2 inputs. The first hidden layer is created because hidden is set as 64 above hidden units. So this is the first layer. This is the activation for that layer. Every layer will have an activation. Dropout, I am going to come in a moment. And similarly, there is another layer. And then there is an output layer. So this is the output layer. This is the hidden to hidden layer. And this is the input layer. Input hidden layer. Okay. So this is the, this is one, this is another segment, and this is third segment. So we add all of that. We get 2240 weights. This I'm telling you so that you know that in the current story, there will be billions of weights in a real life network. Just to make you understand, there will be billions of weights. So here there are only 2,240 weights, and that's it. So now I have not, I think you will understand how the network is created and how the data is flowing. But what is this dropout business? Let's spend 5 minutes on understanding dropout. Now you know that there are so many weights involved. See, what happens sometimes is in a training platform, if it is possible that out of this 64 neurons to these 32 neurons, certain neurons start dominating, meaning the weights associated with those neurons become very high. High weights to certain neurons. It may happen. The imbalance can set in during training, that it so happens that the way the data is and the way the training happens, some of these neurons, maybe we really don't know who, may start dominating the proceedings. They become very weighty. The weights associated with them become very high, and they start controlling the output. And what that does to the network is that it leads potentially to what we call as overfitting, because in general they have learned the training data so well and overemphasize the training data into some of these weights that the other neurons are basically not influencing the output adequately, and that becomes a problem. And invariably, as we later learn, this leads to a phenomena called overfitting, which is a very potentially dangerous phenomena in artificial neural networks. So the trick is that
how do I ensure that certain neurons don't dominate the proceedings? I ask some of the neurons to be absent. That means they will not produce any output. They'll be connected and all, but their output will be all zero, and it will be driven by the dropout. So they will not influence the output for some of the training cycles, for some of the training loops, by ensuring that they fall silent, and therefore they cause loss, and therefore the other neurons start picking up and their weights get increased. What happens is the weights get more or less uniformly distributed across all neurons, or simply speaking, all neurons start getting importance when the output begins to depend on all neurons and not on certain neurons. See, it's like saying that how do you make a class intelligent, right? Now, an intelligence of a class, if it is dictated by only a few smart students, and as long as those smart students are there in the class responds well to an external examiner as a whole. It's basically because only a few students are responding well and they are influencing the output. It shouldn't be like that. That is called an overfitting, because if those guys malfunction, then the whole story goes wrong. So what do? If we discover such smart students are there, we ask the smart students for a few days randomly to stay at home and ensure that still the class continues to respond as a whole properly. And if we are able to train our class to respond properly or well, in spite of the absence of certain so-called smart students, we end up making the entire class smart. That's the basic theory of dropout. So don't allow certain neurons to become very important and their weights to enhance substantially, which is bound to happen sometimes. Ensure that everybody learns equally and no neuron becomes a heavy neuron or an important neuron, and everybody is kind of given opportunity. Basically, you absent some of the smart kids once in a while on a random basis from a classroom and ensure that the class performs uniform. Did you get this idea of the dropout? Why the dropout is introduced in the layers? Why we make randomly some neurons to fall silent? Are we clear about the dropout idea? It's an important principle to understand. Yeah? Is it clear? Is dropout clear? Okay, good. At least one guy says it's clear. There are no messages. Okay, fine. Okay. Now I want you to understand the idea of dropout. Okay. That's important. Okay. So I'll pretend that you have understood. And now we'll see the model in a little more detail. Yeah, you can remove. Yeah, so this is the net, and the forward is the method of the model, which is normally called. So in the forward method, we just build the network. So this is the net, the same net here. So we just build the network and create the network. So this is the creation of the ANN. ANN also called as an MLP. That is the name. Multi-layer perceptron. It's 2 layers. Okay. No, Emaduddin, it will just randomly make some guys fall silent. It is not biased towards weight large. No, it's not. Random. It's random. Okay. Yeah. Okay. Now going down. So now the model. See, remember we had shifted the data to the device earlier. The data set to the device, and now we are shifting the model, this model which is going to execute, also to CUDA. Okay, we want the model to run on GPU. I think data we have not shifted yet. Huh? Data has not been shifted yet because data we have just put it in the data loader. But the model, this model will run on GPU. So it's shifted to the GPU. It is done by this line. Of course, this is if only that GPU is available. Okay. So this is what is meant by creating a model. So we have achieved creating of the data. We have creating of the data loaders. Creating data, then creating of the data sets and the data loaders, creating the model. Now we'll move to the next step, which is we will now create in a very simple way criteria, which is the cross entropy loss, and an optimizer, which is based on Adam, and provide all the parameters. Okay. Now, before we go there, a few things about the cross entropy loss and a little bit about its understanding. Now, we are using a different loss function. We are not using the MSE loss. We are using the cross entropy loss. So let me just explain what is the cross entropy loss. Okay. Okay. Let me write this. It's a very interesting way of producing this. Now, if you recollect our network, let's work. Then let's work our understanding of the network. At the input for every sample, we have two attributes. Then at the ANN first layer hidden, we have 64. So this is 2, this is 64. Then we have a second hidden layer, which is 32. And finally, the output is 2. Now, the way the output will be produced, in our case, when we design the network, is there will be two values which are produced for the output. Okay, so this will be called logits. There will be two numbers which is produced for the output. Remember, the output is supposed to say these two outputs represent whether this belongs to the whether this particular input belongs to which class, whether it belongs to the first class or the second class. So ideally, if it belongs to the second class, it should produce a high number here and a low number here. I'm repeating. If the input sample belongs to the second class, which is the second moon, then it should produce, this represents the first class, this represents the second class. So the value which should be produced for this, let's call this Y1 and let's call this Y2. These are called logits. Okay. So Y1 is low and Y2 is high. Means what? That the sample X, in this case, X belongs to the second class. Correct? Y1 is low. The number produced for the first class is low. The number produced, this is how these networks work. The number produced for the second class is high, which means think of it like some kind of a probability. But probability it is not, because probability is always limited to 0 to 1. This is some kind of a number which implements what is called the likelihood. So Y1 is low means this class is less likely. Y2 is high means this class is more likely. That means if it produces a low value for Y1 and a high value for Y2, then we say that the data belongs to the second moon. That is a second category. On the contrary, if Y is high and Y2 is low, then we say it belongs to the first category because Y1 is high. This is the signal for Y1. If that number is high, that means it belongs to the first class. This indicates the relative value which decides whether this input sample should be classified as Y1 or Y2, as belonging to the first class or second class. That dictates on the relative values of the value which is produced for Y1 and Y2. If the Y1 value is high and Y2 value is low, it is that. If it's neither this nor low, then there is a problem and we have a loss kind of a thing which is there. Now the cross entropy loss measures the log probability of how close Y1 is to Y. I mean, how close we are to the answer. Basically, if the way it measures it is, now if it produces entropy, this is a two-class classification. So let's say it produces a number 31 here, and it produces a number 2 here. Okay? Then what I say is, obviously this is the big one, but it should have probably been higher. So I produce minus log. Okay. Now what happens internally if these numbers are produced? Okay. There is a little more logic that happens internally to the cross entropy, but I think I will not go so deep yet into the cross entropy. I'll leave it to yet another session where I discuss these loss functions in detail. But at this stage, I think you should understand that what I'm measuring here is a way of deciding whether the data belongs to the first category or the second category, the first moon or the second moon. And I'm deciding, I have two outputs at my disposal, and I'm going to decide it on the basis of the relative values of Y1 against Y2. If this is very high compared to this, I say it is first sample. If not, I say second sample. And obviously, I'm going to compare with the way the value is there in my Y. My Y, remember, says only 1 here and 0 here. That is my actual Y which is given. Okay. The prediction which is going to be produced is 1 or 0. So somehow this 31 will be converted into a value, and it will be measured against this 1, 0. I will tell you very briefly what it will be measured. It will be minus log of 31. Okay. So that is what will be the loss. Okay. Now what does this mean? Okay. Now imagine that I produced, okay, imagine I produced a wrong answer. Now you'll have to think a little with me here. Imagine I produced a wrong answer. What would a wrong answer look like? A wrong answer would look like I produce a very low value for Y1 and I produce a very high value for Y2. That would be a wrong answer, because originally the answer given for this data is it belongs to the class 1. So it should have produced 1 or 0, meaning a very high value here and a very low value here. But imagine that our network is producing for Y1 a value which is very low, then it would be wrong. And a value for Y2 very high, then it would be wrong, because this is 0 here and 1 here. So now how does this translate into this? Okay. Now, if I have a wrong answer, the wrongness of the answer, the degree of wrongness of the answer is, look at it this way, minus log of 0. Okay. Very small value, 0.0002. Okay. So, and now let's try to compute this. So this is, you know, from logarithms, this is can be written as log of a very high value, because this will become log of 0.002 to the power of minus 1. So it will become log of 1 by 0.002. So this produces as a result a log of a high value. Log of a high value when I say to the some base a will also be a high value, right? So because a to power of some high value will produce a high value. So what does this mean? In this case, the loss will be very high because the cross entropy loss measures the loss. Why is the loss very high? This gives the loss minus log y. In this case, will produce a loss where y is the expected answer. I'll explain this in a moment. This is important to understand. If you understand just this part, I think you would have understood a lot. I'll elaborate this. I'm saying this again. Let's say my neural network is going to produce two values in the output. If the answer is going to be, and how many classes are there in my output? 1 or 0. Those are the only two classes. So this represents the first class, this represents the second class. Y1 represents the first class, and Y2 represents the second class. Ideally, if the sample belongs to the first class, Y1 should be very high compared to Y2. Okay, this is the basic thought. Now, if Y1 is supposed to be very high compared to Y2, what I measure is for whatever is the correct value. Now I take this is the correct value, right? This is supposed to be very high, right? And if it is wrong, okay, this will be very low. If I'm producing a wrong answer, this will be very low. So if it is a low value, then minus log of y will give me the loss. It will always give me the loss. So I mean the low value, okay, whatever the value here, okay, I will call this y1. So I have to measure minus log of y1. Okay, now in this case, if y1 is very low, signifying a wrong answer, okay, this is very low means I've got a wrong answer because this should not be very low compared to this. And if I'm producing this very low, what will happen? Log of 1 by a very small value will produce a large number, and log of a large number will be a large number, and therefore the loss will be very high. It is a log loss, but the loss will be very high, right? If the loss is very high, and it should be very high in this case because I gave a wrong answer. On the contrary, if my answer is right, what does my answer right mean? That this value is very large. Y1 is very large because the ultimate class is the first one. So the Y1 is very large. When the value is very, very large, what does minus log Y become for a very large value? So log of very large value becomes 1 by Y. If this is very large, okay, this becomes very small. If Y is very large, 1 by Y will become very small. Okay, it will shrink, and a to the power of 0 will be equal to 1. So it will come down to the loss will drop in that case because this will become a very small value because this is large value. 1 by Y will become a very small value. If you take a log of that value, that will also be very small. So what it means, then in that case, the loss will be very small. Okay. So this is how this works. Okay, I don't know how many of you caught this, but this is important to understand because this is how logics work, and this is how cross entropy loss works. I'll talk about this at length when I go through the loss functions, but the simple idea is if I give a wrong answer, my loss should be more, and if I give a right answer, my loss should be less. So if I'm giving a right answer, what does it mean? This value will be higher, very high. If this value is very high compared to this, and it will measure the relative high of this with respect to this, if this is a very high value, then the log minus log of that value will be very small. Minus log of that value will be very small. So that is the loss. So the loss is supposed to be very small because I have kind of got the answer correct because I gave a high value for Y1 in my training, in my network. Okay. So idea is if the answer is going to be the first class, then y1 value should be very high compared to y2 value. If my answer is supposed to be the second class, then my y2 value should be very high compared to y1. And by measuring the log of that value, which is supposed to be the correct value, I get an understanding of how much loss I'm having. So if the loss is very high, that means my answer is very wrong. And if the loss is very low, my answer is coming close to the right answer. This is the argument and justification behind cross entropy loss. We will talk at length of cross entropy loss, but this is just to give you a first level intuition. Okay. So anybody understood how loss works? Yeah, okay, good. If you are getting that, okay, there was a question in the meanwhile. What if due to random the weights which are large are not removed? Well, you have to take the chance. That's why you have to keep on testing. This answer is to Pujita. See, we just have to take the probability. We can't say only drop neurons whose weights are high. No, we randomly choose so that the balance is retained. I think that answers your question, and somebody else also asked a similar question earlier. Will drop out only deactivate neurons? No, dropout is immune to the actual weight. It will randomly pick some neurons and disable them. It's not based on what weights were given to the neurons in the earlier iteration or the so far iteration. No, it doesn't depend on that at all. Okay, so it is completely without that. Okay, so I think you understood cross entropy loss to a certain extent. We will talk at length, but think of it as predicting the degree of wrongness or rightness. How wrong I am will be dictated by the cross entropy loss. So if I'm very wrong, the loss will be more. If I'm very right, then the loss will be small. That's the basic philosophy. Okay. Now, I think we have to go to the next line. That is also a very important line, and let me now elaborate on that line a little more. This is the line I'm talking about. Now, this decides two things. You know, how the gradient is computed, and how the learning rate is used in computing the weight update. Now, those of you who have refreshed this a bit, I will tell you now at a gross level how the Adam optimizer works. First of all, see what are the parameters to the Adam optimizer. They are model dot parameters. Model dot parameters are the weights which are getting used, which are going to be updated as a result of the training. As a case in point, let's bring the size of model dot parameters, or let's just print the size of model dot parameters or the length of model dot parameters, just to get a hang of how it will take the bias probably also into consideration. So after that, just print. No, don't do the okay, you can set the optimizer. You can say print model dot parameters dot size, I guess. Model dot parameters.
Dot shape or size.
Not size, I think, or length.
Will run entire thing.
No, don't run the entire thing.
Like this.
Will be length. Length object.
Model has name.
No, model is created now.
Oh. Yes, sir, but it doesn't have parameters as, okay, spell.
Parameters is a,
No,
no, and it's a method, I think. Call the method and then returns an object, and then we need the size or shape of that object. Method. Just say shape or length. Just say length. Length should work. LEN. No, you have to say what is model.parameters. Anybody knows what's the length, or I don't know what is the data type which is written.
Parameters, whether it's an iterator.
Is it length? LEN. Just try LEN.
Just let us see only parameters also. What it will return. It returns an object.
So we need the size of that object, right? Length of that object. They may have, some student may only do it. Length, yeah, that's what I thought.
Model dot parameters.
Length.
LEN.
LEN. Length on the bracket. Length bracket lo model dot parameters.
LEN will do.
Extra one bracket.
Extra. Correct.
No, length also doesn't seem to.
Right.
Oh, just say parameters without the method, right? That
Incorrect.
no, one more bracket, Baba.
Parameters is a method.
No, parameters is a method. So
Method has no length.
Parameters dot length put model dot parameters dot length put dot length.
Then method.
No, we tried that.
Dot length put.
yeah, we'll have to convert it into list and then find. Say list and then do it. What are you doing?
It's converting that into list and getting the size of the list from parameter model dot parameters.
No, make that model dot parameters into a list. May work.
Total params in the
Colon missing. Sir.
Yes.
Just say list, it will become a
Length of list of model dot parameters.
list. Model dot parameters first becomes a list and then
After getting the list. Unexpected indent network. Select 4 measure. 1.
So indent.
6.
There are 6 parameters.
6. Why 6?
That's why we get that 64, 64, 32 for each param. What is the length?
What is the length of each layer?
Oh, the number of parameters are 6.
6. And the one which I tried.
Oh no, but then we need to get each of them.
Each of them is this.
Achha, this is the length of the list.
Yes.
Okay, they give parameters.
This is what?
This is each param's length. There are 6 parameters.
Yeah, but this doesn't make sense, no? See, we have a network with no, yeah.
This is parameter.
The parameter and the length of the parameter complete.
Its tensor and its value.
They are spread into those tensors. The size of each tensor is 64.
64, 64,
2
32,
into
32.
64.
Overall is being done.
Means that first layer, secondary layer, and
third
last
layer.
So first
All the
layer
6
is
layers.
what?
64.
First layer is 2 into 64. No.
Oh, that's right. 64 appeared twice. X and Y.
No, I think
32 came once, 32 came twice again.
it's not the X and Y thing. It's now the weights. There are two inputs, so the weights should be 2 into 64, and somewhere we should capture that.
Do you want the names of the parameters?
No,
Names
names don't matter.
Okay.
Yeah, I think we'll worry about that later. So basically, we will worry about the structure of parameters a little later. Let's go back to the code. Let's finish this part. Yeah. So yeah. So let me just basically stop with explaining just this line, what it happens here. So basically, well, we will figure out the data structure a little while later. Basically, this refers to all the weights in the various layers. We are saying all the weights are put under the Adam optimizer because for all these weights, the gradient has to be accumulated on a batch level. Gradient accumulation has to happen. And once the gradient accumulation happens, basically the gradient will have to be summed up, that is the accumulation, and applied to update the weights, applied to update weights at every batch, after every batch. Now, who is going to do this? This is going to, see, when we wrote the code, we used that delta and all of that to walk our delta backwards based on the proportion of the weights and all that. Now, we are not going to do that any longer. We are going to ask this optimizer to compute the loss and do the dou L by dou W for every weight, because unless somebody computes the dou L by dou W using the chain rule for every weight, we cannot conduct an update to the weight. This also remembers the momentum because Adam remembers the momentum also. And also it understands that though I am starting with this learning rate, as I reach closer to the answer, I have to do a learning rate decay, okay, by a certain specified value, which can be passed as default in this case, or I can pass it as a decay parameter also. So what the Adam is going to do is for each of the weight parameter, it is going to compute internally the dou L by dou W, which is the gradient of the loss with respect to the weight for each and every sample, accumulate it for all the weights, and we'll instruct it to do it. And also at the end of every batch, we'll see how that happens. At the end of every batch, apply that dou L by dou W accumulated gradient to update the weights using a learning rate, which is initially LR or 0.01, but over time has to be made to decay. So the usage of the momentum, remember we talked about momentum in an earlier session, where the earlier updates should influence the current update. That is what we talk about as momentum. That is the update which are applied in this batch don't depend only on the computed gradient of this batch, but also include the computed gradient for the previous batches, and all of that is influencing this thing, the update that we are applying. So all of that is being taken into consideration by the Adam optimizer. So we don't have to go about applying the chain rule like we did in the
programming using from scratch. But the reason for doing that is to illustrate to you how the delta is computed and how the delta is propagated backward. But now with these libraries, with these advanced libraries, we just have to say how the loss is to be computed. This decides that. And we have to say how the weights are going to be updated by just saying, I want the Adam style of weight updation. So that comes with its own algorithm of computing momentum, own algorithm of computing the learning rate decay, and takes that and applies it to the weights to change them after every batch. So that's what it does. Okay, I think this is what we were looking for. The print.model.parameters.size is what we were looking. This you put or what?
No, sir. My-
This is in the PDF, right?
No, sir.
Huh?
It's not in the PDF.
Achha, this is your line, so this is not working, right?
Yes, sir.
Okay, so this is not there. So, okay, so this is the code, which is now we are deciding what loss to use, and we are deciding how the loss is going to impact the weights by not writing any code, but deciding to go for the Adam optimizer, which internally will do exactly what we were doing earlier, which is using momentum, using the gradient and using the decay on the learning rate. All of that it will do, but it will hide all that nitty-gritty from us, and it will keep our code clean. Okay. So now I'll just do the training loop and then we'll stop just to show you. So we have decided what to do, and no, what are you going to do?
What the parameters will be displayed.
Okay, let's see what does the optimizer do. So he's printing the optimizer. So these are the various things that are done. The learning rate is starting with 0.07. Now the weight decay is currently 0, but you could set it to something. If you use this, I guess, so this influences, this parameter influences your momentum. This influences your learning rate decay. You can customize this by giving parameters here. Okay. Okay. So anyway, we'll not go there yet. Yeah. Now I'll just show you the training loop and just understand how simple it is. Can we go down? Little bit. Little bit. Okay, this is enough. This is enough. Okay. Okay. Now we start the epoch training. This you understand, we'll ready to stop. Just I'll take 10 minutes. So we have created the model. We put it in the training mode. Put it in train mode. Then initially, obviously, when the first epoch starts, basically the running loss is 0. The number of correct predictions are also 0. The number of total predictions are also 0. Now what do we do? Okay. Now remember we had created a loader which goes to the data set and picks up data 64 at a time. So XB, YB brings 64 samples and their predictions and their output from the training loader, which in turn brings it from the training data set. Training data set has a lot other samples, 1000 samples. So 64 at a time are being brought from the data set into the loader. The loader will manage automatically using the batch size. Now these samples are pushed to the GPU, because remember your MLP, that is your trainer, the multi-layer perceptron, has already been shifted to the GPU. So while currently the training loader works only on the CPU, the data batch wise, this one batch of data, that batch of data is now shifted, transferred, let's say transferred. It's transferred to the GPU. So the data is all in the GPU, the algorithm is also in the GPU. Now remember in when we used to do the gradient computation, at the beginning of every batch, we had to zero out. So we're just beginning the batch. we are zeroing out the gradients because the gradients are accumulated only for a batch. So the gradients are done. The zeroing of the gradients is done. Remember, for this we wrote code, but now it becomes so simple using the Adam optimizer, which we just instantiated. Then we compute the logics, which is the compute the y1 and the y2, and then using the logics and the expected y, this is the y which is expected, which is the ground truth as we call it. This is the ground truth, and we measure y1 compared to the ground truth, y2 compared to the ground truth. If the ground truth is 0, then y1 should be very high. If the ground truth is 1, y2 should be very high. All of that is measured in the criteria. Criteria, remember, is the loss function. So I compute the loss using this y1, y2 values, which is the logics, and the expected y, which is 0 or 1. So the logics are just two numbers, and depending on 0 or 1, we check whether if it is 0, this should be very high. If it is 1, this should be very high. And we take the log of that, minus log of that, to measure the loss. If you get that. So if this is if the answer is to be 0, then this is to be very high, and the loss is therefore minus log of y1, because that is expected to be high. So this is the loss. If this is high, then the log of this will be low and loss will be low. Okay, so that is what loss computation will be. So I'll compute the loss using this logic, and once I have computed the loss, I will backward propagate the loss. You see, just one step. This will this will compute all the deltas, and based on the weight to which the deltas are connected, it will take the loss backward. It will compute the deltas backward, and then optimizer.step will take the computed loss which has been, so this will compute dou L by dou W for each of the weight, and optimizer.step will basically do what? Because you're doing the model at the batch level. At the end of every batch, it will apply this dou L by dou W based on this and the learning rate and all of that. It will apply a correction to the weight, because all the weights are under the control of the optimizer. Remember, we gave all the weights of the model to the optimizer. So loss.backward will compute dou L by dou W. It will take the loss and use chain rule to propagate the loss backward. You already know how to do that. And once you know how the loss is propagated backward, using the loss or dou L by dou W, we'll have to update the weight using the momentum and all of that. So the actual weight update is done in this step. So this is propagate the loss or back propagate the loss, and optimizer.step carry out the weight update. All of this we had done from scratch earlier. Okay, so just see, in just 2 steps this is being carried out, nothing else. Just do loss.backward. All the deltas will go backward and you'll get dou L by dou W's. And then you just do optimizer.step and it will apply the weight updates just in one line. We don't have to do all those delta computation and all that. That's the power of using tensors and using the library and all of that. So now what do we do? I'm just going to do this and we're going to stop. This is basically the training loop. It's super important to understand this loop. And this is just some data which we are accumulating. So we are converting the loss from a vector into a scalar and multiplying the loss with the batch size and saying if this is the loss, multiply that loss with the number of samples. Then predict what are the predictions depending on the logics, dimension 1, Logits, you remember, logits has y1, y2. This is the thing. We pick up the maximum argument of that, and then compare that argument with yb, 0 or 1, which is the argument which is highest, and compare that with yb. So if that is matching, then we have a correct prediction, and then we measure, add to the total the batch size, and keep these statistics. This is just accumulating the statistics. Can we go down? So the running loss is accumulated every time, and the accuracy is accumulated every time. So for every epoch, the loss is running loss by total. This is done for all the batches in the epoch. The training losses are overall training losses across all epochs are appended, and all of this is brought. So this is what is called training. And then comes the issue of evaluation. Well, you have the code. Look at the code for evaluation, because I think I'm exceeding the time. But this is the training loop. Okay. This, whatever we have done so far, is called the training loop. Okay. Now I don't know. I went in a little hurried manner, but this is, I wanted to get that to understand, so that we can grow on it in the next session, because this is fundamental. This you'll do again and again whenever you are developing any network, whether it's a CNN or an RNN or anything. This code will repeat. So I'll pause at this stage without loading too much, because already the session has gone into 2 hours. Are you getting some sense of how do you train a real network? So should we do a poll or what? Yes, one person understood. Very good. We're just asking us, so far so good. Just respond so that we know where to stop, where to end, where to begin.
37 votes.
Only. Yeah, we would like to hear more. Only 31 people have voted.
32 plus 38.
38 people have voted. Okay. Okay. I think lastly, you seem to be getting it. It's good, because all of this is necessary for understanding AI. Okay, fine. So in the next week, next Sunday, that is, I will talk about how the evaluation happens and how this code goes forward into some plotting and drawing and all of that, so that you get a hang of that too. Okay, so this is a complete program which basically starts with training and then testing and then all of that, then plotting and typical loop. So you should know how to write this loop at least for one program and get the idea. Okay, so we'll stop here and continue in the next session, next Sunday.